Think of rockets, we think of fail-proof systems. And luckily for us, that's the case most of the time. There's a stage in the overall process known as propulsion testing. Propulsion testing basically works on testing out the rocket engine to make sure that there are no major flaws or inefficiencies before the launch vehicle is actually in flight. In 2017 in McGregor, Texas, the Merlin engine was being tested out. A test known as a LOX drop was conducted. A LOX drop is basically adding a little bit of liquid oxygen inside of the rocket engine just to make sure that there are no leaks. When this was conducted, the whole Merlin engine actually managed to ignite and explode. Did this not only create financial setbacks, but it also slowed down the development of the Falcon rocket? What if I told you there's a way to fix this? And that's with computational fluid dynamics. Let me briefly talk about that. Computational fluid dynamics is basically simulating fluids in an artificial environment. What's so advantageous about this whole process is that it's fail-proof. You can try different parameters and even try different designs to make sure that the efficiency is reached for whatever your needs are. I decided to simulate the exhaust plumes of a rocket engine due to my passion for just rocket propulsion in general, and specifically advanced methods of rocket propulsion, such as antimatter propulsion and fusion and fission propulsion. I decided to use a software known as ANSYS Fluent. ANSYS Fluent works on basically creating a visual interface for users to use to make sure that they are able to see and understand what's happening in their simulation. I chose the software because of this feature, alongside just the wide variety of different options you have with what you can do to your model, such as meshing, and alongside just different features with face splitting, which I'll mention in the next part of this video. Okay, so this is ANSYS, and I'm kind of just going to go through each of the steps that I have in the whole process. So yeah, let's just start. So first of all, we have like our geometry. So for that, I'm just gonna go here because this is my geometry. So if you can see the cursor, then this part is the actual nozzle, and this edge right here, that would be the connection between the combustion chamber and the nozzle. So that's where the flow is going to start. And the rest of this space is basically known as a shock domain. So the exhaust is going to flow through here, and you can see and then this is the shock domain, or representing the area around the nozzle. So for this, I just did a few sketches, one just simple sketch right here without the face split, and then one with the face split. The face split is basically just me splitting the overall geometry into a couple of faces to make it easier for meshing, which is the next stage. So this is my mesh. So meshing is really important because it maintains accuracy inside of the model and also speeds up the overall calculation process. So it is a really important stage. So here you can see my mesh. This kind of just shows like where the exhaust would flow, and then this is the separation between the shock domain and the exhaust flow, this little line in the middle, as you can see right there. And then I created name selections. Name selections are basically just letting the model know what part of the geometry is what. So the pressure inlet, which is right there, the pressure outlet, the far field, so it's part of the shock domain, and the nozzle walls, or what makes up the nozzle. The next part of the overall simulation was the like the actual solution part of it. So here I've selected density based, and then the rest stays the same. If you load it in Fluent and then the solution page, you would see the rest be the same. I just changed the type to density based. Then for models, I turned on the energy equation, which is normally off for this specific project. And then since K epsilon is the most commonly used model for turbulent flow, that's the one that I selected, K epsilon, and then I selected the realizable model for the K epsilon model. And then click OK here. Then I clicked on materials, or fluid, and then air. Here I just changed some of the models as per the simulation. So here I just changed it to ideal gas as the density, and then the Sutherland model. These are both accurate models for this type of project. So that was that. And then boundary conditions. So boundary conditions, here you can see all of the different boundary, like the name selections I created. Then what we have to change is the pressure inlet. So Just waiting for that to load. And then we would also have to do the pressure outlet. So here I just listed my gauge pressure and then thermal in the temperature in Kelvin for the inlet. Same thing for the outlet. I'll just show that quickly. Here, same thing, the gauge pressure and then the temperature in Kelvin. So those are my boundary conditions, or what the model will use to basically start the flow. Then you go into the reference values. The reference values is basically just there, just check if the values that I input in the boundary conditions are accurate. So here you can see similar gauge pressures as before, and then the Kelvin is similar as well. So we're good in that area. Then we click on initialization. We just compute from our pressure inlet, which is where it's going to initialize the overall model, and then the flow will start to form. Here, then I just clicked run calculation. I had 5,000 iterations, and then the time steps were already, I just used the standard time steps. Then you click calculate. You should see a graph called scale residuals that will show you how the flow is starting to form. In the middle, actually, you click on graphics. You can stop the calculation and you can resume it later. I clicked on graphics and then I clicked on contours. And then I just clicked velocity and then Mach number here. And you can see the flow starting to form. Save/display, and you can see the form starting to flow for half of the nozzle. And then that's basically where my solution was done. Okay, so after the solutions page, we have our results right here. So you can see the whole flow has developed, and I've just mirrored one results to the other just to create the full exhaust flow. So the simulation was successful, although the point of the simulation was to observe potential inefficiencies inside the rocket nozzle, and we can clearly see that here. So basically, to first of all get the stage where it's at, you create a contour, which is basically just showing the flow from before, and then you select what variable you want. So in this case, I was looking at velocity, so that you have that, right? And then now you can see the contours, I mean the Mach numbers on the side, and then the overall exhaust flow right there. So you can actually see shock diamonds. Shock diamonds are like these discs, or of course, as the name suggests, these diamonds that are visible in the exhaust plumes of the rocket engine. And this occurs when the atmospheric pressure is higher than the exhaust gas's pressure, and this causes there to be shock diamonds. It's really like it happens a lot with testing on ground. So you can see shock diamonds in a lot of ground testing for rocket engines, and even at lower sea level. So that's kind of what you see there with the shock diamonds. And another thing is that looking at the flow, the Mach numbers do fall off at the end, meaning that it isn't the strongest flow. You usually want stable, like a stable pattern with the Mach numbers. And so kind of it's probably because the flow isn't the exhaust plumes aren't fast enough. So to probably boost this, I would compress the throat a little bit more just to get at the speed of sound. Although these two are just some inefficiencies with this rocket engine, and it kind of just shows you like the potential that CFD has in analyzing these aspects to make sure that your rocket engine is efficient as possible. About it for the simulation that I created. I hope you enjoyed the video and kind of saw the potential with CFD in the space tech industry and how it's basically promoting the faster development of rockets. And my interest with this is potentially using this for advanced methods of rocket propulsion to enable interstellar travel. I've also linked my Medium down in the description below. There's an article version of this video if you want to read that as well. And consider following my Medium for future space tech related articles. Until then, I'll see you next time.